you enjoy it. If you're interested in the project and want to learn more, the full master's thesis and source code is available on my GitHub at the link below. I'm also looking for openings or other opportunities in the industry as I'm finishing up my studies, so feel free to reach out to me there or via email. Note that the email address is without an L. Now let's get going with the presentation. Here's today's agenda, pretty straightforward. We start with the introduction and objectives of the work. Modern networking divides into a hardware-based data plane for packet forwarding, a control plane for routing, and the slow path connecting them. OVS, an open source option, manages this interaction. While efforts have focused on optimizing the data plane with hardware, the slow path has been overlooked. Recent studies show it's becoming a bottleneck in high-speed networks, suggesting it could benefit from dedicated acceleration like hardware offloading. Optimizing OVS is key for SDN, especially when unknown flows cause cache misses. Cache misses trigger costly upcalls to the control path, where new flow rules must be added. This introduces latency, particularly in dynamic workloads. Frequent upcalls from small flows, referred to as bursty, further strain system performance. My thesis optimizes OVS by predicting traffic and preloading flows into the cache, reducing latency from slow path upcalls. I benchmark OVS across various scenarios to identify improvements and analyze its behavior to guide future research. My research explores how much OVS cache performance can be improved using branch prediction to predict and preload flows. The first objective is to analyze the impact of preloading, while the second is to assess OVS performance across various traffic scenarios. Now let's quickly go over some background. The OpenShift Container Platform, OCP, is Red Hat's Kubernetes distribution, offering a consistent foundation for managing and scaling containerized applications across hybrid and multi-cloud environments. Its networking architecture integrates OVS and Open Virtual Network, OVN, to manage network resources efficiently, using OVS as the virtual switch to ensure reliable connectivity and dynamic resource allocation within Kubernetes clusters. OCP also supports deployment across on-premises, cloud, and edge environments, allowing organizations to run applications across different infrastructures. Co-flows share attributes like destination or temporal location, grouping-related data flows, and cluster computing. This method is ideal for optimizing communication in data-intensive applications like MapReduce and Spark. By aligning flows with application-specific semantics, co-flows improve resource utilization, allowing for better scheduling and allocation compared to traditional networking. They also offer visibility into higher-level communication needs, reducing completion times and boosting overall performance in large-scale cluster environments. A co-flow can be thought of in more practical terms as the collective network activity generated by a single application. First, the DNS resolution, which constitutes the base flow. Second, associated flows initiated by and related to this base flow may include an HTTP GET request. And if the page has dynamic content, it requires database server queries. Finally, further interactions like submitting data on the page add additional associated flows. All these flows together constitute a so-called co-flow. We'll get back to co-flows shortly when we get to the methodology used in this work. Previous research shows the slow path in OVS, relying on general-purpose CPUs, becomes a bottleneck at higher speeds like 200 gigabits per second due to latency and cache saturation. As traffic and flow rules grow, performance becomes inconsistent. To address this, a domain-specific accelerator is proposed, offering faster table updates, predictable response times, and larger memory pools. This work aims to contribute to this area of research by further exploring solutions to enhance slow path performance. To improve OVS scalability, Raschelbach and colleagues introduced a neural network-based cache that accelerates packet classification through predictive rule matching. This approach leverages shallow neural networks to perform inference, allowing fast identification of rule matches as packets arrive. The cache adapts dynamically, with periodic retraining to integrate new flows as they are added, ensuring high accuracy and reducing latency. They tested two integration methods. The first adds this new cache as a secondary layer, while the second fully replaces the control path, enabling direct classification of open flow rules without slow path upcalls. The second approach achieves speedups up to 12.3 times over standard OVS, making it highly effective in environments with large and frequently updated rule sets. Some researchers are starting to recognize the performance advantages of having future insights into cache demands. Seer takes this idea forward by predicting upcoming data requests based on network packet delays. When packets are queued at neighboring nodes, Seer captures metadata like flow or object IDs from these packets and sends it ahead to the target caching node. This metadata acts as an early warning system, giving Seer insight into which data will soon be needed, even before the packets arrive. By using these advanced notifications, Seer can prefetch necessary data and make smart eviction choices, transforming packet delays into valuable prediction windows and significantly reducing cache misses. The result? Seer delivers up to 80% fewer cache misses than traditional methods, leading to faster data processing and flow completion times. Building on the performance gains shown in both Nuevo Match and Seer, this project explores how their caching and prediction methods could be integrated into OVS to enhance its efficiency and performance. The goal is to assess how feasible it is to bring these advanced approaches like future-aware caching into OVS to potentially boost its performance. Beyond that, the project also aims to contribute a framework that encourages open-source collaboration on developing a flow predictor for OVS, creating a motivational foundation for ongoing and future improvement and innovation in the open source community. Now let's look at the methodology used to benchmark OVS. We're focusing on three key metrics in our benchmarks: latency, CPU utilization, and upcall statistics. These measurements help us understand how the system performs under different conditions and where potential improvements can be made. In this figure, we see the benchmarking environment showing the two interconnected servers, SUT and the traffic generator. The system under test, SUT, runs OVS 3.3 and OVN 23.6.2 in a virtual machine, equipped with Mellanox Ethernet network interfaces capable of handling traffic at 100 gigabits per second. On the other side, the traffic generator uses FastClick with Data Plane Development Kit, DPDK, to simulate high-speed network traffic, providing the necessary load for our performance tests. Here we see an OCP cluster used to benchmark OVS. The system under test replicates a single-node OCP setup with a simulated OVN environment, bypassing network address translation to allow direct access to external service IPs in the dedicated subnet. In this setup, we deploy 8 pods, each assigned unique IPs for internal and external communication. These pods are configured with load balancers using UDP ports to mimic both pod-to-pod and external service communication. On each pod, a custom-designed daemon runs to parse network packets. More on this later. To benchmark OVS with realistic traffic patterns, we use a workload generator based on the Synchronia framework. It upscales a Facebook map-produced trace, allowing adjustments to the co-flow count and network load, while preserving the trace's original characteristics. One key concept we introduce is co-flowiness, which measures how interdependent flows within a co-flow are, based on shared destinations. This can range from 0, where all flows are distinct, to 1, where all flows share a destination. To ensure even traffic distribution, we modify the generator to balance traffic between the two subnets. This is done by mapping IPs using modulus reduction. We also define base flows as those with a destination port of 2100, separating them from associated flows, making it easier to analyze the co-flow trace. Flow size distribution plays a key role in benchmarking OVS by representing the amount of data transferred in each flow, affecting the number and size of packets transmitted in the network. These distributions are generated from cumulative distribution functions, providing a realistic statistical model for flow size sampling and are based on real-world network traffic data. In particular, the Facebook Hadoop distribution, with an average flow size of 122 kilobytes, reflects large data transfers typical in data processing environments like Facebook's Hadoop clusters, testing OVS's ability to handle substantial data exchanges with long-lived stable flows. On the other hand, the Google Search RPC distribution, with a mean flow size of just 426 bytes, captures short, bursty flows common in remote procedure call scenarios. This is useful for evaluating OVS's latency performance under highly dynamic, bursty network loads. In the figures on the right, we see probability density histograms of the two distributions. Note the difference in the x-axis where the Facebook distribution is made up of more large flows. To measure the latency of OVS, we insert unique packet numbers and timestamps at the ingress and egress of the cluster. These points, shown in orange and green in the figure on the right, are where we use an XDP program to modify the network packets to track how long each packet takes to travel through the system. The UDP packet payload, shown in the lower figure on the right, is structured with three 64-bit fields, a packet number, an ingress timestamp, and an egress timestamp, totaling 24 bytes. The daemons, mentioned earlier, run on each OCP cluster pod and are responsible for parsing these packet fields to gather latency statistics, storing the data in an array for further processing once the benchmarks are complete. Now, let's dive into the benchmarking setup used to evaluate OVS performance. In the baseline scenario without flow prediction, we clear the data path caches, set a flow limit of 200,000, and transmit the entire trace, collecting metrics continuously for analysis. In the optimal scenario, with flow prediction, the caches are preloaded with associated flows, and only base flows trigger upcalls, maximizing performance gains. Additionally, we adjust the ratio of associated to base flows and modify trace properties like flow size distribution to assess their impact on OVS performance. All the ratios we used are shown in the table to the right, and this is what we refer to as co-flowiness. Remember this term, as it will be important later on. The traffic generator transmits co-flow traffic to the SUT at 12 gigabits per second, repeated 10 times per co-flow configuration, the two flow size distributions, resulting in 7 unique benchmarks per distribution. A Python script parses JSON files from the receiving daemon to calculate minimum, maximum, and average latencies. These include metrics for the first packet of each unique 5-tuple base and associated flow, as well as latency for all packets processed by fast-click and observed by OVS. Now let's look at the results. Here we see the results for the first packet of each base flow. Each box plot represents a specific co-flowiness configuration on the x-axis, with latency on the y-axis. As we study the figures, we can see that increasing co-flowiness generally reduces latency. This happens because OVS handles fewer associated flows, as base flows aren't preloaded. Notably, the Facebook trace shows a clearer trend and consistently lower latencies compared to the more bursty Google trace. There are also a few anomalies, which we'll address later. On this slide, we see the results for the first packet of each associated flow. We can see that although Google and Facebook are very distinct datasets, latency is drastically reduced as the co-flowiness level increases beyond 0.5. In the baseline scenario with a co-flowiness value of 0.0, the Google trace has 58% higher maximum latency compared to Facebook. Moreover, for intermediate co-flowiness values, Google shows 1.6 to 2 times higher maximum latency when compared to its counterpart. When all flows are present, as in the optimal scenario, their latency distributions converge, which is expected since no upcalls are required. Here, we see the aggregated mean latency results from all packets, not just the first packets. For the Facebook distribution, there's a clear trend of decreasing latency as co-flowiness increases. While the trend is also visible for Google, it's not as pronounced. In the worst-case scenario, the mean latency for Google is over 10 times higher than for Facebook in the base setup. For intermediate co-flowiness values, Google's mean latency remains about 5 to 10 times higher than Facebook, demonstrating a 30% improvement when 25% of the flows are accurately predicted. At a co-flowiness of 0.75, the mean latency for Google is 15 times higher than that for Facebook. In the optimal scenario, the mean latencies for both FSDs converge, which is expected since all flows are fully cached. Now we move on to CPU utilization. The upper figures show kernel CPU utilization and CPU usage due to software interrupts. The lower figures represent total CPU utilization, including those two factors and more. it's easiest to focus on the lower figure. Here, we see that increasing coflowiness reduces CPU utilization, but only for the Facebook distribution. For Google, only the optimal scenario shows a decrease in utilization, while all other coflowiness configurations place the same load on the system. For Facebook, we also observe lower CPU usage over time as more flows are cached, but this pattern doesn't hold for the Google distribution. Next, we look at the CPU resources used by the OVS handler threads, which manage upcalls. The upper figures show kernel and user space resource utilization, while the lower figures display total utilization. Interestingly, Facebook shows higher resource usage than Google here. However, as coflowiness increases, Facebook reduces its resource usage, which Google does not. The lower resource usage in the Google distribution is due to batching upcalls, which introduces latency. We will explore this further later. Here, we see CPU utilization caused by the pod daemons. While this doesn't directly affect the performance results, it's important to consider since it impacts the total CPU utilization shown in the previous figures. The key takeaway is that daemon load is twice as high for the Google distribution, and it increases over time for the Facebook distribution. Lastly, we have the upcall statistics results. On the left, we see Facebook, and on the right, Google. They look different because the Facebook trace takes much longer to transmit due to its larger flow sizes compared to Google. The key takeaway is that for Facebook, upcalls per second decrease over time and they start immediately, while for Google, upcalls occur later due to batching. We'll discuss this batching behavior in more detail later. With the results now presented, it's time to dive into their meaning and explore why they look the way they do. Low coflowiness causes frequent cache misses and upcalls, especially with bursty traffic like the Google trace, leading to higher latency. In contrast, the Facebook trace, with its larger, long-lived flows, reduces latency even at lower coflowiness. As we increase coflowiness, latency drops further, especially for Facebook, while Google sees smaller gains due to its bursty nature. At higher coflowiness, nearly all flows are cached, minimizing upcalls and converging latency for both traces. However, Google's short-lived flows still limit caching effectiveness, requiring higher levels for noticeable improvements. Due to an error when constructing the coflowiness configurations, the number of unique flows differs between them, as seen in the lower figure on the right. This difference causes latency anomalies. Higher coflowiness levels result in more unique flows, increasing system load, and generating more upcalls, which skews the latency results even though the total flow count remains constant. The upper figure shows an anomaly for the 0.25 coflowiness value. Additionally, while the distribution of unique flows is relatively even, small differences across tests can still contribute to these anomalies and impact caching efficiency and latency. In the Facebook trace, caching reduces upcall frequency during runtime and CPU utilization as coflowiness increases. Over time, fewer new flows enter, minimizing CPU load and software interrupts. In the Google trace, short-lived flows keep upcall frequency and CPU usage high. Even with higher coflowiness, rapid new flow arrivals limit caching efficiency, sustaining CPU load. For batch processing, the Facebook trace shows a drop in upcalls as flows are cached, reducing CPU utilization. In the Google trace, upcalls, software interrupts, and CPU load remain high because OVS is batching packets, which increases latency but optimizes CPU usage per upcall. Google's higher daemon load compared to Facebook results from smaller packets, increasing the number of packets per second, reducing queue depths, and raising CPU usage for network stack processing. Google's bursty traffic spikes CPU utilization and resource contention, in contrast to Facebook's steadier flow and more efficient caching. Despite similar entry rates, Google's bursty traffic leads to higher CPU demands, while Facebook's consistent flow allows for reduced batch processing and lower CPU usage. Google shows a 90% increase in daemon CPU usage compared to Facebook, indicating that additional factors contribute to the overall CPU load difference. Flow rate, defined as the number of new flows per second, plays a crucial role in OVS performance, directly affecting upcall frequency and latency. High flow rates, like in the Google trace, lead to more upcalls and higher latency, unlike the slower Facebook trace. Frequent upcalls cause CPU bottlenecks, delaying flow entry installation and increasing processing load and latency. OVS upcall handling operates like a queuing system, where the flow rate must stay below the processing capacity to avoid overload. If flow rates are equal under similar conditions, latency distributions converge. The number of upcalls exceeded 200,000 observed flows, meaning multiple packets from the same flow caused upcalls before caching. With TCP, this is avoided since no additional packets are sent until the synchronized packet is acknowledged. We used UDP, but TCP behaves differently due to the synchronize and acknowledge exchange. TCP's connection-oriented setup spaces out packet arrivals, allowing the initial synchronized packet to trigger an upcall, while subsequent packets wait for the handshake to complete. This design allows time for flow entries to establish, reducing unnecessary upcalls like with UDP. As a result, TCP's retransmission timers and delayed acknowledgements lead to fewer upcalls and lower CPU usage, which translates to better upcall management and improved OVS performance. The benchmarks used a synthetic trace, which simplified the setup but didn't fully reflect real-world OpenShift deployments, leading to some anomalies. The simulated OCP cluster lacked realism, missing flow table complexity and true traffic patterns, impacting CPU and throughput measurements. Throughput was capped at 12 gigabits per second due to OVS limits, far below real-world 100 gigabits per second setups affecting the results. Lastly, the performance gains measured excluded real-world overheads like added latency and CPU load, reducing their practical applicability. Future research should maintain consistent flow counts for accurate latency measurement, using real-world traffic traces for better assessment. Actual OCP environments will expose flow table complexity and CPU usage. Dynamically preloading flows at ingress will provide real-time latency data. Developing flow prediction models using statistical and machine learning techniques is essential for optimizing flow preloading. Additionally, leveraging GPUs or FPGAs can reduce latency, and benchmarking cache-integrated systems will help balance performance and resources. Now, let's quickly recap the work. This research focused on addressing OVS performance bottlenecks caused by cache misses, aiming to improve efficiency by preloading future flows to reduce upcalls. Benchmarks showed that higher coflowiness, especially with the Facebook trace, reduced latency and improved cache hits. As coflowiness reached 90 to 100%, both the Facebook and Google traces saw latency convergence, though some anomalies appeared. Google batching reduced handler thread load but increased latency, showing that flow rate significantly impacts OVS performance, particularly in upcalls and latency. Thanks, that was all I had today. Thanks for listening. Do you have any questions?
Okay, thank you. If anyone does have questions, I believe Elko will be answering them on behalf of Emil. So are there any questions from anybody here?
Sorry?
There's one online.
Okay. What is it? Oh. With some precedents of attack vectors utilizing branch prediction in CPUs, what type of assurance would it take to mitigate crafted packets giving an elevated unintended data access? And would those mitigation make the performance gains possibly moot, like in the CPU comparison? I'm trying to understand the question a little bit better. All right, so I think the question is, if we need to mitigate attacks, would it basically, get rid of the advantages that we would gain with the flow prediction? I think that's a good question. I don't know the answer to that. I don't think we try to figure out what additional overhead that those attack vectors will take. So yeah, I'm not very sure what to answer there.
Okay.
See one more question here.
Just do you have some examples of maybe how this coflows look like? Like what kinds of additional flows are getting installed after the app call?
Yeah, I don't have the examples here, so I think there are the same type of traffic patterns. So it would just be for us it would be UDP traffic, but they would go to a different pod. So I think what the goal of the co-flow, I think there's a whole paper on it, is that they try to figure out what the associate flows are of a base flow. So let's say someone tries to interact with a website, and then when they do the interaction, there will be maybe database transfers. And then what the co-flowiness means is that, okay, if you have a specific flow, there might be 4 or 5 instances of traffic going to a database server, and then it might go, I don't know, to a different server to get some other data. So I think the idea of the co-flowiness is to represent that kind of stuff. So rather than represent only the user-initiated traffic, it would also represent the associated traffic with that user interaction. So going to that website, to that pod for the website, that pod will then connect to a database server. And then after the database server, it might go to a different database server. So they try to group that together. And I think the different profiles are based on the different study where they figure out, with some traffic traces taken in a Hadoop cluster from Facebook, what are the associated traffic there. So.
Okay. Any further questions, either in the room or online? Okay, I guess we're done. So let's thank our speaker,